What the heck?
Tagon.
Welcome to
Wacky Calc Wednesday!
And today we're going to do something that I haven't covered in quite a long time, and that I thought would actually not be possible for me to solve explicitly, but it turns out it's actually not that hard. It's really quite easy, and I'm surprised that I didn't just do it in the moment. So some of you may recall from quite a while ago, I did a response video to Dr. Payam about his videos on product calculus or multiplicative calculus. And one of the questions that I had for my productive equations, which were equations involving product derivatives, so like differential equations but involving product calculus, was, are there any functions whose regular derivative is the same as their product derivative? And I got to a result that said, if that function exists, it would have to have the property that the logarithm of its derivative is the same as the derivative of its logarithm. And I just thought that wouldn't be analytically possible to solve, because when I plugged it into Wolfram Alpha, it gave me an implicit solution. But it turns out Wolfram Alpha just wasn't being creative enough. And it works out just fine. Because I plugged this into Desmos, and then I did log of f prime and log of f primed, right? Derivative, dived. And they both gave me the same curve, which means it must have worked. So let's explore this result, because it's a very neat solution. It's in tune with our recent W extravaganzas, and it's some seriously wacky calc. So let's do it. Alright, so let's simply just recall the derivative of the function f as a function of x is by definition the limit as h goes to 0 of the difference quotient, right? F of x plus h minus f of x, all divided by h. The product derivative is very similar. You can actually write it notationally like this, df to the power of 1 over dx. And that does work out mathematically. And what it turns out to be is, by definition, is the limit, very similar to this actually, the limit as h goes to 0 of f of x plus h divided by f of x, all to the power of 1 over h, which is quite neat. And so what you can actually do is rewrite this as e to the log of this thing. So we get e to the log, but because of the way convergence works and all that jazz, you can exchange the limit and the logarithm, and so you get the limit as h goes to 0 of the log of this stuff, and the power comes down out the front, and we get the 1 over h there, and we get log of f of x plus h minus log of f of x, all divided by h, and this is actually just the derivative of the logarithm of f of x. So as it turns out, the product derivative, as it's defined, is the same as e to the power of the derivative of the log of f, whichever function f you pick. And as it turns out, this extends to all indices of derivatives. So if you wanted the nth product derivative, right, you could just do e to the nth derivative of the natural logarithm of that function f. And so all I had a question about that I didn't answer in the original video was, what if you have a function whose regular derivative is the same as its product derivative, which is not too difficult to figure out once you realize that you just need the Lambert W function. So what I'm asking is, since the product derivative is defined as e to the power of the derivative of the log of the function you're thinking of, then the question is, find the family of functions f of x such that the derivative of f is equal to the product derivative of f, which is e to the derivative of the natural logarithm of a function, which is the same as f prime divided by f. And all I did at first was just take the log of both sides, so we get that log of f prime is equal to f prime over f, which is of course the same as the derivative of the log of f, the logarithmic derivative of f. And so essentially what we're saying is if the regular and product derivative of a function are the same, then it must also be the case that the logarithm of the derivative of the function is equal to the derivative of the logarithm of the function, which is a very interesting thing to ask. Very interesting indeed. But we're actually going to keep this form because it'll be easier to work with. What we're going to do is we're going to divide f prime to the other side, and then multiply both sides by -1 so that I can write 1 over f prime inside the logarithm. So we're going to get 1 over f prime times the logarithm of 1 over f prime. But to get the 1 over f prime in there, I had to multiply by -1. So on the right side, I'm going to get -1 over f. Right? This 1 over f stayed, and then we're multiplying by -1. And now I can apply the w function to both sides, and I'm just going to get log of 1 over f prime. So I apply the w function to both sides. I get w of -1 over f is equal to log of 1 over f prime. Of course, we want to solve for f prime in terms of f, and so we're going to raise e to both sides. And we're going to get that, this is going to turn out to just be 1 over f prime, but of course we can just reciprocate both sides and get f prime equals e to the negative w of -1 over f. So we have that the derivative of this function is equal to e to the negative w of -1 over f. Very, very neat, very, very strange looking thing. But all we have to do is now multiply this term over to the other side and solve using separation of variables, right? So we just multiply this over, and we have, and we'll write f prime as dy dx. So now I'm writing f as y instead. So and then we're multiplying e to the negative w, well it's not negative anymore because we multiplied it over, e to the w of -1 over y, and we're integrating, so I have to multiply the dx over, so we get separation of variables, right? And we're simply just solving a regular differential equation now. It's a little weird that we have, you know, w in there, but it's not too difficult to do. So of course this one is just going to come out to be x plus a constant. That's not too difficult. So what we have so far is that we have x plus a constant is equal to the integral of e to the w of 1 over y, -1 over y, sorry, dy. And all we're going to do is let u equal w to the of -1 over y, which tells me that u times e to the u is equal to -1 over y, which tells me that y is equal to -1 over u times e to the negative u, because I have to reciprocate and then multiply by -1, and that tells me that dy is equal to, what do we have? We have the derivative of the first part, which is 1 over u squared times e to the negative u, plus 1 over u times e to the negative u. Right? That's very nice. And that's dy, right? And then we have to multiply it by e to the u, right? So we end up with this integral, e to the u times e to the negative u times the quantity 1 over u squared plus 1 over u du, which means that this simplifies drastically. These cancel, and now we just have to integrate these powers of u, which is really, really nice. So the reason I could do this, by the way, is because this is the inverse of the w function, so that's sort of the reason I was able to do that. And then we just have to use the fundamental theorem of calculus, and we get minus 1 over u plus log of the absolute value of u. And then, of course, this is equal to x plus a constant, so I'm not going to bother with the constant down here, but now we simply have to plug u back in, and u was w of -1 over y. So we have that x plus a constant, so therefore, x plus a constant is equal to, and remember y is the function we're trying to solve for here. That was the original f that I had stated before. I'm just much more used to using y as a variable of integration. So we have, and we really don't, we're not going to bother with the absolute values. But I'm going to make this negative as well, so what I'm going to do is I'm going to have a negative here, and I'm going to have 1 over u on the inside like that. And so what we end up with is minus 1 over u, so minus 1 divided by w of negative 1 over y, minus the natural logarithm of 1 over w of negative 1 over y, like so. And now all I'm going to do is multiply the negative 1 to both sides, like so. And now what we're going to do is we're actually going to raise e to both sides of this equation. Because notice what happens. This becomes e to the log of something, which just gives me that thing back, right? And then we have e to that thing. So I end up with 1 over w of negative 1 over y times e to the power of 1 over w of negative 1 over y. Which is just brilliant because I can now use the w function to cancel this, which is just crazy. So by the way, e to the negative c is just another constant, so I can rewrite this as a constant times e to the negative x, right? That's totally fine. But now I'm just going to apply w to both sides to solve for this inner part here. So we're going to get w of some constant times e to the negative x is equal to this thing out here, is equal to 1 over w of negative 1 over y. So of course, we want to solve for y as our general function of x, right? So we have to reciprocate both sides and then actually apply x times e to the x on both sides, because we're going to have to get at y, which means we need to cancel the w function. So first we need to reciprocate, so it's got to actually be the other way around. We're going to have 1 over w of a constant times e to the negative x equals w of negative 1 over y, and then we need to apply u times e to the u on both sides to cancel this w function. So we end up with 1 over w of a constant times e to the negative x times e to the power of 1 over w of a constant times e to the negative x equals negative 1 over y. So we need to multiply by negative 1 on both sides and reciprocate on both sides. So reciprocate, I just wrote 1 over that thing. And so in the end, we finally get our result. The answer to the question of which functions have the same product derivative as their regular derivative, it's y equals negative w of a constant times e to the negative x times e to the power of negative 1 divided by w of that same constant times e to the negative x. And this is the family of functions that satisfies y prime equals, I don't know what the product derivative is, we'll just do y to the power of a star, or like an asterisk or something. So this is the same thing as e to the power of the derivative of the logarithm of y. And this is the family of functions that satisfies that relationship. It's an incredibly cool set of functions. Varying c doesn't really change, it's not that, it's a cool answer, it doesn't look that cool, honestly, but it's a neat answer nonetheless. So if you took the derivative of this function, or you took the derivative of the logarithm of this function and then raised e to that power, you would get the same result, because that's saying that the regular derivative is the same as the product derivative. So even though that was quite symbol heavy, as per usual, my beautiful, beautiful audience, I hope that's clear. And look at that doggy. He's so cute. All right, stay tuned for this. Going to be doing analysis soon, so I hope everybody's looking forward to that. I'm going to make a series on those things, and I'm going to very soon get into one of these two papers, which involves understanding Bernoulli numbers and Euler's summation formula, and also an extension of tetration to complex heights. So I'll be getting into those rather soon, but I'd also like to get started on my analysis series, because I'd really love to sort of reinforce my knowledge about analysis and go through it myself, because what better way to learn something than to teach it? So thank you very much for watching, everybody, and I'll see you all again soon.